relations that are missing out if you go Hartree-Fock.
Okay.
All right. Thanks very much. I think we have to move on. My time is already down to 5 minutes for the last talk. And of course, we try to be on time somehow, so I will not keep you very long, I guess. So, Dimitris, can you please stop sharing the screen?
I've stopped, yeah.
You stopped already. Okay, so it's still showing here. Because what I want to do, it is to just basically cut this short and to show you what we've been doing recently. So our main idea was to now, after doing these kind of first simulations, that
We don't see your screen, Dieter. Sorry, we don't see your screen.
Oh, you don't see my screen. Sorry. You see it now?
Yes.
Okay, so the idea was, after our first simulations, to see whether we can actually also do boundary conditions. And we, of course, started with the simplest possible scenario and looked at how easy or how difficult it is to implement boundary conditions into the kind of general structure of the matrix product codes that we did before. And then to look at how they would scale compared to standard direct numerical simulation, to see whether these codes can, in principle, then give us an advantage on the quantum computer if it were implemented there. And so what we looked at was this kind of simple example where we here have a lid that is just a box, and the top lid of that box is moving at some speed v. And so for different speeds v that we get here, we would have different Reynolds numbers defined by the speed of the lid. And what we looked at was the flow field inside of that box. And now if you look at this, so kind of what do you expect in the simulation to happen? Well, as the lid moves up here, of course, you have up here those lid conditions, and eventually here at the front, a big vertex should form, and this vertex gets bigger and bigger and bigger, and eventually will fill out the whole volume if the lid goes fast enough. And so what we looked at was how well can we simulate this using matrix product states. And so just very briefly, what we used was the stream function method for this. So we had the Navier-Stokes equation rewritten in this form with some potential psi. So this is this kind of stream function psi, and the flow fields u and v, and the Laplacian of psi is minus the w. This would be the vorticity in this case. And then you can rewrite this Navier-Stokes equation in this form here. And what we then want to do is we want to evolve the vorticity in time through these two partial derivatives with respect to x and y of two functions f and g that are the products of this u times the vorticity and this mixed derivative here and g the other way around. And we did this in a two-step predictor corrector McCormick scheme, which I think I've been told multiple times now is not the best way to do this, but still that's what we did, just for proof of principle. And what we then need to do is we need to update the stream function by solving the Poisson equation in this way. And so what we now did with this approach was to take these equations and step by step just convert each bit of them into a matrix product state. So we basically have matrix product descriptions of u and of v and of psi and of w. So all of these terms will be written as matrix product states. And then we update these functions through this kind of more or less standard method that is used in fluid dynamics all the time to evolve these types of steps. And so a couple of things that are now visible here is what is the kind of operations, what are the kind of operations that we need? I mean, these are listed here. So basically what we need to be able to do, we need to be able to add two functions. So that appears up here, that appears down there. So we need addition. And what we do is variation and addition of two matrix product states. Matrix product states are not forming subspaces. So if you add two matrix product states, the bond dimension can change. So you don't stay within the same subspace of matrix product states. So what we do is we add them. That first of all blows up the bond dimension, and then we compress that back down to the bond dimension that we want it to be. And that's an operation that scales like chi the bond dimension cubed. And then we have to multiply different of these functions together. So this is not a multiplication of simple matrix product states, but this is a point-by-point multiplication of the functions that are represented by these different matrix product states. And this appears, for instance, here, where we have to take u times v or v times w and so on. And there is a multiplication algorithm that again works with combined variational method. So basically what one has to do there is one has to turn one of the matrix product states into a matrix product operator via so-called copy dots, and then multiply them together and then compress it again to get rid of the high matrix product bond dimension. And that is something that we could only do with a scaling of chi to the 4. So that basically is what provides us with the bottleneck. This chi to the 4 scaling is really what is most slowing us down. Then we need a Poisson solver. So we need to solve the Poisson equation as is here. There is an algorithm for that in matrix product states in some publication 23, which is referenced in the original publication that we have. That goes like bond dimension cubed. And then we need just some standard matrix vector multiplications, for instance, for working out these partial derivatives. And that's something which scales like bond dimension cubed times the bond dimension of the matrix product operator that we have. So typically these matrix product operators will have some bond dimension that is fixed. This is independent of what state one has. Like there's a certain bond dimension of a Laplace operator, certain bond dimension of some first derivative and so on. And these bond dimensions turn out in our case to always be less than 6. So the one that is the biggest bond dimension is the bond dimension of the Laplace operator is a dimension of 6, and all the others have smaller bond dimensions. So these are pretty small matrices that one needs to deal with here. So really the main scaling comes from this multiplication of two functions that appears here and there. And then basically, yes?
Is the 6 due to the two-dimensionality of the problem?
Probably yes. There would be 8
9
or so.
or something like that.
8 or 9 for 3D. Yes. Yeah. Probably. I mean, yeah, because it's two-dimensional, it will be higher dimensional, but it's not much higher. It's just
Of the same order.
It's of the same order of magnitude. Yes. And so this still here is preprint. It's on the archive now. I sent it around. But basically, these are the scalings that we have, and then we just take this and step by step realize this as a matrix product algorithm, and then we compare how well this works compared to the standard method that one usually uses. And here just show some of these matrix product operators. How do we work them out? Well, there's a very compact way of noting them down. So for instance, if we have forward differences here just in the x direction, the matrix product operator would be some kind of vector A, some vector C, and then in the middle some vectors, some matrices B. Each of these matrices has 2 elements. So in each of these terms, so 1 would be identity matrix with 2 1s in there. Sigma 0 1 would be this matrix. Sigma 1 0 would be that matrix, and 0 would just be a 2 by 2 0 matrix. So this overall would be a 4 by 4 matrix. And those are the matrices you multiply together, and then you get one big matrix that basically then, if you apply it to a matrix product state, gives you this kind of forward difference. So that's how we build those up. We build up those matrix product operators just from individual matrices, small matrices B of k, as shown here, or some matrices B of k here for the Laplace operator. And you see these are a bit bigger, and they would probably get another 3 entries here if they were in 3 dimensions. And those you program once, and then you just reuse them. So we don't need to get them all the time. They are kind of geometry dependent in this case, of course, for fixed boundaries. So there's no periodic boundary conditions here. These are fixed boundaries. That's why these matrix product operators have these terms A and C at the ends. So the beginning and the end is dealt with differently to the interior points because we have not periodic boundary conditions, but hard boundaries. And these boundary conditions on the sides are encoded into this first and this last matrix that you get there. Okay, so yes.
A brief question. If we have now the grid spacing in X and Y is H, the isotropic homogeneous
Right.
spacing. If that changes, then you reuse these operators, or do you have to
Then you have to change that. So this is,
every time?
no. If as soon as you fix your geometry, you would keep them, so they are the same for one geometry. But as soon as you change the geometry, they will change. And what mainly would change is here the values that you enter. The shape would still be the same, but of course
The structure would be the same, but you could automatically say
right.
generate them.
Exactly. So if you ask how do you generate those, there are these. Yeah, I saw that question. So there is this kind of automaton method that's been developed in quantum physics, and there is one PhD student of mine whose name was Paolo Bosson, who did this 5 or 6 years ago. He's got a whole chapter in his thesis where he explains how these automatons work. So what you write down is basically you write down an automaton that tells you how to move from one side to one step to the next, and on what path you pick up one operator. So basically then this you can see as having initially two initial states, and then you move either one way or the other way, one way or the other way. You move to this automaton thing, and that basically then just multiplies all these matrices together. And you can via this automaton way, you can more or less automate this generation of matrix product operators. You define the rules once of how you get from one place to the next, and then you just simply run the automaton and you build up these matrix product operators. Essentially, it's for free. Okay, but yeah, it's here we've done it for these examples. Probably you need to do this for different examples. In quantum physics, this has been done quite a bit, and we've been using this a bit. But that's what you typically get out. You typically get out pretty small matrices for these differential operators. They don't blow up. They typically stay small, a couple of entries into these matrices. And that's also the reason why operating with these on the matrix product states is reasonably efficient. This really is quick, and much quicker than one might think, because it is a highly compressed notion. We also did this in 3D. So what I showed you is 2D. We also did this in 3D. This is just looking at it from two sides. So you see that basically here a big vertex forms in the center under the lid, and we compared these solutions to existing solutions on the web, and it turns out that they are very, very good. So here, for instance, we get errors in the continuity equation that is on the order of 1%, and in the momentum equations, which is about 1/3%. And these calculations were done on a 256 by 256 grid for, however, a limited Reynolds number of 1,000. And if we do that and then compress again our state as we discussed today, what we find is that we need a maximum number of chi that is roughly 200, and this corresponds to a compression of 95%. So out of the overall state that you need in order, if you wanted to do a direct numerical simulation, you only need about 5% of the values of the kind of real numbers, so to say, to characterize these flow fields. So it's a massive saving in memory. You save about a factor of 20 in memory when storing the flow fields in this compressed way, and that actually is one of the advantages, one of the attractions, because that of course also means that your memory description of the state fits much more easily into cache. You don't need to communicate that much, and that typically speeds up some of your computations. And so we look, yes.
So basically what is required is only the grids and the physics, no data.
No data, no grid and the equations.
Which is the physics?
That's what I mean, but
Yes, that's what we have here.
Or the approximate.
Yeah, and so what we did then was we looked at now how does our simulation compare in this matrix product state calculation to direct numerical simulations. And of course, to be fair on this, we ran this on the same computer. We used some kind of standard DNS code that we have from earlier. And we looked at how does the simulation scale with now the number of what we call qubits again. So basically, the logarithm of the number of grid points would be this n here. Okay, so basically this axis here gives you an exponential scaling in the size of your system. And here we see how the maximum chi increases with the number of grid points that we need. So you see, first of all, it goes up. And then basically here, where the grid reaches the Kolmogorov scale, as you would expect, the chi doesn't need to go up anymore. So we basically reached a place where the whole physics can be described and no more correlations are necessary, and this chi levels off. So this basically shows you that for these type of calculations, we don't really need more correlations to describe the physics. But of course, we can go up with the grid size, and around here at somewhere like 22, that would be where we have the Kolmogorov length scale fully covered. And now we can look at what is the time it takes our matrix product algorithm to run with increasing n. And as you would expect, this goes up linearly. So this is a linear scale, whereas this is a logarithmic scale. So with exponentially increasing system size, our code runs only linearly slower. So the time it takes goes up in seconds from 1 to 5 when we increase the grid size from 2 to the 16 to 2 to the 24. So this is pretty good scaling. That's why we like this, because you can go finer and finer in the grid. And in comparison, the direct numerical simulation that we do is, of course, much faster for small grids. So that takes 10 to the minus 1 only. And then when we go up, it gets slower, it gets exponentially slower. And for this particular one that run both on a laptop, we see the crossover here between the two is somewhere here at around 2 to the 20 grid points, where the matrix product state computation becomes faster than the direct numerical simulation. Yes.
Maybe it's a silly question, but just like before, you mentioned something regarding compression. What do you exactly mean by this compression?
So what I mean by this compression is that if you count the number of entries in the tensor, so all the tensor entries, and compare that to the number of real numbers that you need to store the matrix product state and take the ratio of those two, then that's 1 in 20.
But you haven't applied a Smith decomposition yet.
No, this is done automatically here, because we don't need to apply that. We always stay within that description of Smith decompositions. And of course, here we actually run our algorithm in such a way that the truncation of the matrix product state happens dynamically at the point where the data is no longer needed. So basically, we look at how big are the Schmidt values, and if the Schmidt values go below a certain value, we chop it off in such a way that the accuracy is maintained.
Okay. And the criteria for chopping off is?
Okay, well, in this particular case, the criterion was for the value, for the Schmidt value to be smaller than probably 10 to the minus 5, 10 to the minus 6. So that means you square it to get an accuracy of 10 to the minus 12 or so, which we thought was good enough. But you can, of course, play with that. Okay, and that basically then gives you this 95% compression. And now what we did, we just kind of did take the ratio of those two times, and you can see for small grid sizes, direct numerical simulation is faster. At about 19 or 20 or so, the matrix product state becomes better and it outperforms.
Is that the Reynolds 800, right?
It's 1,000.
1,000.
Yeah, yeah.
And it was never worse than 10 to the minus 1. But 2 to the 16 is what the lowest you checked was 2 to the 16.
2 to the 16 is the lowest.
Per axis.
I think this is per axis, yes. Yeah, I think it's 2 to the 16 by 2 to the 16 with 32 qubits. Yeah, I think so. I think the total number of qubits is 2n for the two-dimensional case. It's 16, 16. So 2 to the 16 by 2 to the 16. Yeah. So it was never really worse than that. And so what we see here is that kind of a head-to-head comparison of disparate numerical simulation and this matrix product states, we get pretty close. But of course, it's not a full-scale comparison in the sense that we haven't tried to optimize either one or the other very hard. We've taken kind of standard DNS code, we've taken our standard NPS code, and the two are compatible. So it's kind of, yeah. But of course, if you go to larger grid sizes, if you have to go to larger grid sizes, then eventually this scaling, the linear scaling, will always win over the complex scaling. There is no doubt about that, except when the chi shoots up here, then of course it won't. And that is the big question. Does the chi ever need to shoot up or not? So in other words, how well is this kind of nice poem that the large eddies only feed on the smaller ones and so on, how well is that in reality true? If that is fully true, then you would never expect the chi to explode. And then you would always expect the matrix product state algorithm to win out eventually because the chi would saturate at some point. But of course, we don't know that. Yes.
But if you chop off, do you know which dynamics that are? So is the boundary layer chop lit, where you lose resolution? So is there like a spatial mapping of the Smith values you lose?
No, there's no space. There's no direct spatial values. There's a length scale value. So in a sense, then you could argue that what you lose out mostly is direct interactions between long length scales and short length scales. That's what you chop off. But you keep all the interactions between the short length scales. You can keep all the fine structures, but you can't basically, if you have little eddies that look very different because there's a big eddy around or there's no big eddy around, then that you would be able to capture.
Okay.
Now, I'm not an expert enough to be able to tell you how sensitive would little eddies be to the presence of a large eddy or not, but I suspect this isn't very.
From what you referenced today, this poem, big eddies being until this property seems to be a pretty localized phenomenon. So you walk down the stair step by step instead of taking 5 steps at once. And for many physics, that's admittedly the case.
Yeah, I mean, so that's what I was hoping. Unfortunately, this is a poem, not a theorem.
It's relative to the wall.
Yeah.
Yeah, there you will see.
This is.
I just wonder, sorry, again, but 2 to the 24, to me, this is about 16 million. I don't.
Yeah.
And 16 million times 16 million on a PC, how can that work? What kind of DNS solver, what kind of magic machine is that? You know what I mean? Because 16 million times 16 million is actually quite a lot of control volumes.
Yeah.
Or points. And on that.
I need to look this up again, but basically we just took the standard thing that we found. We didn't program it ourselves. We just took what we had and just ran it. But I think.
But that is this 2 to the 11 grid site.
Oh, yeah, basically this is this is the total length then. For the total rate, so it's
Okay,
number
so
of
22 is already.
This is both together. Yeah, then it should easily work out.
Okay,
It's
so
hard.
it means 60 million at most, or whatever, 10 or something, that works, yeah.
Okay, so then that's what we have. But on the MPS side, it could easily go up to 48 or 100 or so if you wanted. There's no problem at all. But there's probably no point in doing so, I guess.
So actually, the message is good for me because honestly, I was asking myself, why do you treat the flow with 10 million times 10 million control volume? Everyone will say it's ridiculous. And if you have a method which pays off at that level, no one is interested because that's too much anyway.
That's too much, yes.
But if it is 60,000 control volumes, 2 to the 16 for a coarse mesh, that's reasonable.
Okay.
And if it's 100,000 or 200,000, it's still reasonable. And if you can show that you're doing better at that level already. The earlier the better.
That's true. So we did actually work out where would the Kolmogorov length scale be, and it was
Yeah.
exactly around here. So it's exactly
Yeah,
here.
that's
or
what I
this-
see.
Yeah, so it's precisely here, and of course we don't know whether that's a coincidence or
Yeah.
not.
But what does the Kolmogorov scale mean in laminar flow? A Reynolds number 1,000.
Well, we can just work it out, and
I mean, you can work it out, but
It's just, no,
I mean, there's no structure at that level. It's what is the correlation?
On the other hand, viscous flow dynamics should be at Kolmogorov. Or laminar flow, viscous influences should be at Kolmogorov length scales.
Sure, but this is a 2D flow, so there's no structure other than the main structure.
yes, yeah.
So
and we
you
certainly
you might be seeing. I mean, this might not be representative of what. I mean, you've done a 3D case as well, right?
done the 3D case as well.
Did it ever become turbulent?
We couldn't go long enough in the simulation. We didn't go long enough in the simulation to see
What
it fully
the
developed.
first flow field that's in your head look like?
Zero.
Oh, yeah, we started at 0 and just speed up the.
Did you ever go to Reynolds numbers where it would be
No,
at 1,000? You not like to see that?
no, you wanted to go to 25,000 or so, but we haven't been able to do that.
I mean, if your cost function is dissipative enough, you shouldn't see any transition at that, even at those numbers.
We haven't. No, I
Because-
mean, this is, yeah. You're absolutely right. That's what we wanted to do. And so, of course, then the question came up. So if we go to these higher Reynolds numbers and turbulence starts to arise, then we can't compare the two solutions anymore, really, because they should always be different. So how do we then start to compare? How do we know which one is right and which one is wrong? And then basically we didn't really know what to do there. I mean, so it would certainly be interesting to go to the higher Reynolds numbers and just run it, but then we don't have a handle as to how it really works. And that's why we stayed here with the kind of cases where we can compare and we can actually make concrete statements. It works.
You won't be able to run a turbulence case on a laptop. You shouldn't be able to run a turbulence case on a laptop.
Yeah, probably we will. Yes, yeah.
Sorry, yes, that's right.
No, exactly. We won't be able to run it.
And these are, now we're getting more in terms of questions. But did you, these are timings. Did you compare the flow fields?
Yes, we did compare the flow fields. I don't have, well, I maybe have it somewhere.
Yeah, but just.
Yeah, we did compare the flow
Are they
fields to some kind of,
identical?
they were identical, and we did compare them to the kind of, there is a standard solution to that
Yeah,
problem.
you can have this funny
This-
profile.
Exactly, yeah, we compared them. Our curves lie precisely on top of the reference values. So this is
In both cases.
in all cases that we tested, yes. So this was, I mean, accuracy,
Yeah.
we couldn't wish better.
Yeah, I mean, it's an established case, everyone has done that, so that should be.
So that's why we did. Yeah, we plotted it on top of each other. We couldn't see really a difference. So it worked extremely well. But of course, it's as you said, if you really wanted to go turbulent, we would need to implement this on a HPC computer and then do some parallel and so on and so forth. Then it gets a bit more tedious.
But I mean, that flow that you referenced relates to the cascaded energy in the length, turbulent length scales. So I don't know how it relates to a laminar solution.
No, I mean, it probably doesn't. It just turns out if we work out that number,
Yes.
it happens to be, we resolve it exactly at that point.
But this, I mean, nobody understands. I mean, this is something that I don't find in any documentation or any.
But then, so if if we're able to say that there are no structure, then of course it works because you can cut off at almost any mode because you don't have correlation between length scales because there are no.
Yeah, but we can't. So basically here you see that we need to go up to here to get accurate solutions. So we can't just cut off the time.
Function of your resolution with respect to your what's the approximation of the distribution of the.
Sorry to interrupt, but I have to go really soon, actually. So we are over time.
Yeah, sorry. I mean, we should have another chat at some point, but good to see you. Have a good evening. So which resolution do you mean? You meant this chi here?
No, I'm just thinking about the physics
Yes.
of the problem with
Yeah.
respect to, so you're saying, okay, these things correlate at the different length scales, and that seems to line up with where the Kolmogorov scale should be.
No, what lines up is where the matrix product state becomes as fast as DNS happens to be.
Okay, but that could be luck.
That could be that.
So, but at the same time, you've got a the chi.
Time lapse at the same time you cross. Right?
Yeah.
So it's also crossing.
It's also at the same point. Obviously. So that is the funny thing, that basically here this maximum occurs roughly where this occurs. This is maybe luck, but I suspect that this is less of luck. So that's also why I was actually asking that question today. Look at the entanglement structure. Can you say something about where does the flow start to become non-laminar and start to develop some kind of turbulence? Is this precisely where this chi has a maximum? Is it good? We don't know. At least I don't know. Yes.
Last question. So basically, if we would now aim for a higher chi,
yeah,
then NPS would be less suitable or more inaccurate.
You mean that it would be less?
Yeah, so
it mean suitable or powerful?
By chi, I understand the variance between the large scale structures and the small scale structures. All
correlations
correlations, sorry, yeah, correlations between them. Yeah. And since, as I understood today, correlation is proportional to entanglement on a quantum computer, maybe.
Right.
Then, and the MPS is kind of a linear approach in order to get hold of some large dimensional tensors. Then I suspect that when we have a large correlation, then we are kind of limited by the MPS approach.
Yes. Yeah. So basically yes, so exactly. So if this chi here to the power of 4 is what we need in order to generate these matrix product states, whereas this, and so also in the algorithm, you see chi to the 4 is the worst scaling you have. So the actual algorithm scales like chi to the 4. On a quantum computer, the network we need, so all the maps on the quantum computer are independent of chi, so they're all linear in M, except for generating the variational tri-state. And that will at worst scale like chi squared, but of course it could scale better, we don't know that. So that means at worst on the quantum computer, we'd have a scaling that goes like chi squared times log of the grid size. And here we have a scaling log of the grid size times chi to the power 4. And then of course the question is, how does chi go? Here it does seem to have a maximum and go down again. Only if that shoots up, we're doomed on a classical computer, and we couldn't really say what happens on the quantum computer because it may still be doable with a variational network. But it's not the matrix product network, but that we don't.
Yeah, so I still wish to know why the chi max at the upper left panel does decrease after the.
Yeah, that's a very good question that I do not know. But of course, you could argue, I mean, from quantum mechanics, what do you have there? If you change the state through a phase transition, the chi max goes up until you hit the phase transition point, and then it goes down again. So you identify phase transitions through a maximum in the chi. Now here you know that you have laminar flow at some point, and then you have start to develop turbulence at some other point. And maybe this is related somehow, but we haven't investigated this. This would be my idea for what to look at there. Is that kind of chi, is the entanglement spectrum something that tells us about the structure of the flow? Can we actually analyze where turbulence starts to develop by looking at the entanglement structure of the matrix product? But this is just purely a kind of idea that is not for dissemination, not for